Okay, let's take a look at an example of a simple linear regression. And the problem I'd like to take a look at is one that I've captured for you in a data file that I've posted called realestate.xlsx. And here we have data on 150 homes showing the recent selling price and the appraised value. And what we'd like to see is there evidence of a significant linear relationship between these two variables? And can we come up with a model equation that predicts the selling price based on a value of the appraised value? All right, so this is the data file. And as you can see, we have values for just an index number for each house, 1 through 150. And then we have appraised value in thousands of dollars, selling price in thousands of dollars, square footage of the home, and the number of bedrooms. But we're interested primarily in looking for a linear relationship between selling price and appraised value, and to try to predict the value of selling price based on the appraised value. This means that we're going to try to come up with an equation that says price is equal to some function of appraised value. So price ultimately will be our dependent variable, or our response variable. And I'm going to generate the output, this regression analysis, in Excel using the data analysis tool pack, and then we'll step through some of the features of that output, and there are a couple of different segments. So I'll go back and forth between the slides and the output itself. But the first segment of that output is going to be some summary measures on the regression model. And we'll see something called a multiple R value, which is a correlation coefficient between those two numeric variables. We'll see something called the R squared, which is calculated as the square of the correlation coefficient. And it goes by a couple other names. It's also called the coefficient of determination and the goodness of fit. And as you can imagine, since the correlation coefficient has values between -1 and +1, this goodness of fit, or coefficient of determination, will have to take on values between 0 and 1. Values closer to 1 imply a very good fit between our two variables, between our model equation and our actual values of price. And values close to 0 would imply there's no significant relationship. The other thing that's important to capture is that the actual definition mathematically of this R squared, or coefficient of determination, is that it's a measure of the proportion of the variation in the response variable that's explained by the regression line. Let me say that a different way. It's the proportion of the fluctuation from house to house that's caused by just the fluctuation if we were to stay on that straight line, on that regression line that is modeling price in terms of the appraised value. So that straight line is going to have some variability as the points move along that straight line, but the actual house-to-house fluctuation is going to probably be more than that if you just include, random fluctuation of points falling, not on the line. So how much of that variability in the overall response variable is caused by just that mathematical relationship with the straight line? Another measure that we'll see is something called the standard error of estimate, and this is the standard deviation of those residuals that we talked about. And it gives us some measure of how wrong we might be. What's a typical residual we might find of a given point away from the straight line? And because all of this is based on the ideas of sampling distribution and all the things we've talked about in inferential statistics, it turns out that the kinds of concepts we've covered in confidence intervals and hypothesis testing apply. So we can build some kind of a confidence interval around our straight line and apply that standard error of estimate. So we could ultimately say something like we're 95% sure that our actual value of a home that we predict will be that predicted value plus or minus some number of standard errors of estimate, and we'll see how to apply that. All right, so let's go ahead and we'll do this regression analysis in Excel using our data analysis tool pack. So in my data ribbon, I'll go to data analysis, and I will select the regression option, and it asked me first for my input range, for my Y value, for my response variable, and that's going to be the prices of these homes, so under column C. So I'll select price, and then I'll hit Control-Shift down arrow. That'll select my price variable. And then it wants to know the input X range. Where are my values of my independent variable? In this case, that'll be my appraised value of my homes. And I will then select value, Control-Shift down arrow once again. And I did include labels in both of those columns, so I had that label box checked. And I want to select a plot here of my residuals, just so we can take a look at those residuals. And my output, I'm going to go ahead and place it starting in cell G3, just to put it just off to the side of my data set. All right, I hit OK. Excel thinks for a while and then generates this column of output, this section of output data, and off to the right we'll see the residual plot, which we'll look at in more detail in a short while. Make that look bigger. But for now, though, let's focus on the outputs. So as we talked about, the summary statistics, if you will, summary measures on the model include this multiple R value, this R squared value, something called the adjusted R squared that I'll talk about a bit later on, and then the standard error of estimate, if you will, the standard error of these residuals. So the multiple R here, this correlation coefficient between appraised value and selling price is 0.841, so a strong positive relationship. And the R squared value is 70.8 roughly, percent, so 0.708. And that shows that 70.8% of the variance in price is being captured by this straight line model equation in terms of the appraised value of the home. All right, let's look back at the at another section of this output and what it means. Right below the summary measures, we see something called the ANOVA table. That's the analysis of variance, which is a subject that's covered in Chapter 9 of your text that we didn't go into. But essentially, it's a screening methodology to see if the explanatory variable or variables do not have any explaining power. They don't explain any significant percentage of the variance of that response variable. Now, in our case, we only have one explanatory variable in the example that we've been looking at. But you can think of this as a hypothesis test where the null hypothesis is that the variability is completely random, that this model has no power in explaining the variability. An alternate hypothesis is that the model does explain some portion of the variability. So let's see what this ANOVA test tells us. If we think about the fact that this is a hypothesis test, and it's really capturing, again, you'll see terms in here that are SS and MS. This is sum of squares and mean sum of squares. So it's how much of those squared residuals are attributed to the regression equation and how much are attributed to just the residuals themselves. And there is an F test that's taken place here, but ultimately this significance is a p-value. It's a p-value of this ANOVA hypothesis test, and as we can see, it's a very, very small value, 2.3 by 10 to the minus 41. So that's 0 point, and then 41 zeros, and then 2.3, and then a 2.3. So as you can see, it's a very, very small number, much less than a standard significance of 5%. So this would tell us clearly that at least one of our explanatory variables has some explaining power. And of course, we only have one explanatory variable in this example. Let's hop ahead then, and we'll take a look at what's captured in this next table of the regression coefficients themselves. So here's where we capture the values that we're going to use as our alpha and our beta in our straight line equation, as our A and B really, in our model equation. So A is going to be that intercept, that y-intercept, And the b value is going to be that coefficient for the slope of the straight line, the increase in y per unit value of x. And then off to the right of those coefficients, both for the constant and for the slope, we find a hypothesis test. And particularly in the case of the slope, which is the coefficient for the variable, this test is really a hypothesis test that this coefficient is something different from 0, that the slope is something different from 0. Because if the slope is 0, that implies there's no relationship. So when we look at this, we can think of the null hypothesis of saying that no, this slope is statistically equal to 0. And the alternate hypothesis is that this slope really is something different from 0. So again, as we look at our output from our regression analysis, we can see that our intercept value is a 7.708, and our slope, our coefficient for the variable value, which is our appraised value, is 0.948. So as we build this into a model equation, these are the coefficients A and B that we would use. Now, as we go off to the right here, again, we'll see the results of this hypothesis test. So our intercept value, our intercept coefficient, our A in our equation, is a value of 7.708, and it has a p-value of 0.24. And this is high compared to a significance of 5%. And we would say here that this is statistically equal to 0. That this value here is statistically close to 0. And that's okay. For our constant coefficient, it really isn't going to trouble us very much. This is not a slope where having a value of 0 would present a significant problem. In the case of the beta, in the case of the slope of our straight line, right, which is this coefficient for appraised value, it has a value of 0.948, which means that our price is going to increase by 0.948 for every unit increase, every dollar increase in appraised value. Starting out with an anchor point, if you will, of $7.7. Sorry, these are thousands of dollars, so $7.7 thousand. Here, though, the p-value is very, very low once again, 2.3 by 10 to the minus 41. So this implies that even though this number has a magnitude that's less than 1, it is statistically significantly different from 0. So how do we build all of this into our results, into what we can say about the relationship between these two variables? A model equation, if we pull those two coefficients out, is that price is equal to 7.7083 plus 0.9482 times the appraised value. And again, this will all be in the units of our original data. So price in thousands of dollars, appraised value, thousands of dollars. So if we had a house that appraised for $142,000, our predicted selling price, if we plug $142,000 into this equation as the value for appraised value, our predicted selling price would be $142,353. Now, we might want to know how wrong we might be, because this would imply that the point in our scatter plot fell exactly on the straight line. That's what the predicted value tells us. Well, how wrong might we be? If we go to that standard error of estimate that we saw, we could say, hey, we're 95% sure that we'll be plus or minus 2 standard deviations right away from the predicted value. So plus or minus 2 times the standard error of the estimate. So we can say we're 95% sure we'll be within plus or minus 16,000 of this predicted value. And that seems like a pretty large discrepancy, but as you can well imagine, there are a number of things that go into selling price of homes beyond just the appraised value. Okay, just a few words about the residuals. Remember, we generated this plot of our residuals, and the residuals are how far each point falls above or below the regression line. And ideally, if we've modeled everything very well so that all that's left is randomness, we'd like these residual values to be very small, very close to zero. And most importantly, we'd like to see them randomly scattered around that value of zero with no observable pattern or trend or anything like that. And in this case, this is what we largely see, a cloud of data points that are scattered on either side of a value of zero. And you notice there's one very significant outlier here, and some points will fall some distance away. We don't know exactly what the situation is with that one particular house, but in general, the points seem to have residuals that are relatively small and randomly scattered around zero, which is ideally what we'd like to see.